Let's come to the last part of chapter 3. It says that the bisector of the vertex angle of an isosceles triangle separates the triangle into two congruent triangles. You have to take note that we have here an isosceles triangle. Okay? The vertex of an isosceles triangle. So if we are to illustrate that first, let's draw an isosceles triangle. And let's name this triangle as triangle RTU. Okay? And let's illustrate the bisector. And we know that the bisector is originating from the vertex of one angle and it separates the triangle into two congruent triangles. So it must pass through the midpoint. Okay? Must pass through the midpoint of segment RU. And let's name this one as segment TP. Okay? And let's say that, let's have our given. Let's have triangle RTU is an isosceles triangle. That's one. And that segment TP, okay, bisects angle RTU. Okay, and let's show the triangle RTP is congruent to triangle UTP. Okay? Let's have our proof. From our statements and our reasons. So number one, of course, let's use the first given. So triangle RTU is an isosceles triangle. That is given. Okay, what do we know? If triangle RTU is an isosceles triangle, we know that it has two congruent sides. So therefore, RT is congruent to UT. Okay? RT is congruent to UT. And this is because of the definition of an isosceles triangle. Okay? Let's make use of our second given, which is TP bisects angle RTU. Okay? So, sorry. It should be given. And what do you know when segment TP bisects angle RTU? So TP now acts as the angle bisector of angle RTU. And we know that it divides the angle into two congruent angles. So basically, we say that angle RTP is congruent to angle UTP. Okay? Angle RTP is congruent to angle, this angle is congruent to this angle. Okay? And this side is congruent to this side. So, RTP, angle RTP is congruent to angle UTP. Okay? And because of the definition of angle bisectors. Okay? Next, we know that we have already a side and we already have an angle. Okay, so let's look for another part which could be used to prove that the two triangles are congruent. In that case, we can see that segment TP is congruent to itself. That is RPC, reflexive property of congruency. And in that case, in this particular case, we see here that angle RTP and angle UTP are included angles. So that we're able to show that triangle RTP is congruent to triangle UTP by the SAS, congruence postulate. Okay, and that ends our proof. Okay, next theorem is actually an important theorem because it talks about the relationship between the base angles of an isosceles triangle. Okay, so the theorem says that if two sides of a triangle are congruent, then the angles opposite these sides are also congruent. So actually this theorem is also known as the base angles of an isosceles triangle are congruent. Okay, that theorem is simply phrased as the base angles of an isosceles triangles are congruent. So let's illustrate that again. Let's have an isosceles triangle, and let's name this one as triangle MAE. Okay, so given that triangle MAE is an isosceles triangle, let's show that angle M is congruent to angle E. Let's have our proof. We have our statements and our reasons. So for number 1, we know that triangle MAE is an isosceles triangle, and because of our given. Okay, number 2, because triangle MAE is an isosceles triangle, we can say that MA is congruent to EA. So segment MA is congruent to triangle segment EA rather. This is because of the definition of an isosceles triangle. Okay, now so we don't have any information from our triangle anymore, but what we can do is actually to draw an auxiliary line such that this is the bisector of angle A. So we can draw the bisector of angle A, and let's name that as segment AT. Okay, draw the bisector of angle A. And the reason we can do that is because there is only one bisector of an angle. Okay? So, since segment 80 is already the bisector of angle A, and we know that it divides the angle into two congruent angles, we can say that angle MAT is congruent to triangle EAT. And that is because of the definition of angle bisectors. Okay? So, this part is congruent to this part already. And just like what we did a while ago in the previous theorem, is that we can see that segment 80 is congruent to itself. And that is because of the reflexive property of congruency. Let's have our number 6. And we already have a side, an angle that is congruent, and an included angle. We also have a side that is congruent. So we can already show that triangle MAT is congruent to triangle EAT because of the SAS congruence postulate. Okay, and since we already have shown already that these two triangles are congruent, and it follows that their parts must also be congruent, so that angle M is congruent to angle E, and that is because of CPCTC. Okay, we're able to show that the theorem holds. Okay, let's have an example. Find the size of each angle of the isosceles triangle. For letter A, the measure of angle 1 is equal to 36. And the letter B, the measure of each base angle is 5 less than twice the measure of the vertex angle. So first, let's illustrate our isosceles triangle. And let's name that this one is angle 1, this one is angle 2, and this one is angle 3. And since this is an isosceles triangle, this side is congruent to this side. Okay? So for letter A, the measure of angle 1 is given, which is 36. And we have already learned that the sum of the interior angles of a triangle is equal to 180. Okay? 180. So that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is equal to 180. Okay, but what we can infer here is that angle 2 is congruent to angle 3 because they are base angles, and we have already shown that the base angles of an isosceles triangle are congruent. So, but the measure of angle 2 is equal to the measure of angle 3. Okay? So we can just say that this should be, so since they are equal, just plug in the measure of angle 1 plus the measure, we have twice the measure of angle 2 by substitution. Okay, is equal to 180. So just substitute the measure of angle 2 is equal to the measure of angle 3. Therefore, the measure of angle 1 plus the measure of angle 2 plus the measure of angle 2. And the measure of angle 2 plus the measure of angle 2 is twice the measure of angle 2. Okay? And let's substitute the value of the measure of angle 1, which is 36, plus 2 times the measure of angle 2 is equal to 180. Subtracting both sides of the equation by 36, then what we have here is twice the measure of angle 2 is equal to 180 minus 36. What we have here is twice the measure of angle 2 is actually 144. Then dividing both sides by 2, then the measure of angle 2 is equal to 72. Okay, 72, which is also, this is the measure of angle 3. Okay, since they are equal. And for letter B, the measure of each base angle is 5 less than twice the measure of the vertex angle. So let's have our representation here. Let x be the measure of the vertex angle. Okay, and 2x minus 5 be the measure of the base angles. Okay, so again, we know that the sum of the interior angles of the triangle is equal to 180, so that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is equal to 180. Okay, and just plug in. So this is let's say that x is the vertex angle from the given illustration. This is x plus 2x minus 5 plus 2x minus 5 is equal to 180. Okay, to simplify that, what we have is x plus 2 times 2x minus 5 is equal to 180. Okay, then let's distribute 2. What we have there is x plus 4x minus 10 is equal to 180. And adding both sides by 10, what we have now is x plus 4x is equal to 190. Simplifying the left side is we have 5x is equal to 90, and dividing by 5, both sides is x is equal to 38 degrees. And this one is the length or the measure of the vertex angle. Okay, for the base angles, we know that we have 2x minus 5 is equal to, just substitute, 2 times 38 minus 5 is equal to actually 76 minus 5 is 71 degrees. Okay, so this one is for each base angle. Okay. So we also have a theorem. This is actually the converse of the previous theorem that we had about the base angles of an isosceles triangles. This time, let's have its converse, which says that if two angles of a triangle are congruent, then the opposite and the sides opposite these angles are also congruent. So actually, this one is already obvious because we already have shown that if we have base angles as congruent, which therefore it follows that the side that is opposite these angles are also congruent. So we'll no longer prove this Okay, we no longer prove this one. And also, we have two important corollaries and will no longer prove these corollaries. It says that if two angles of a triangle are, an equilateral triangle is also an equiangular triangle, and an equiangular triangle is also an equilateral triangle. Okay,